Alright, let's take a look at a penny or a book or an object sitting on an inclined plane. First we'll draw a picture. This will represent a block, a penny, whatever object we would like to think about. And we want to basically look at a way to figure out mathematically the coefficient of friction between the bottom surface of this object and the incline that it's on. First of all, we do a system boundary to isolate the object. That will be in our free body diagram. Over to the right, we will make a dot that represents the object as a point mass or particle. Next, we will rotate our axis system so that we have an x-axis that is parallel to the ramp, and a y-axis which will be perpendicular to the ramp, like so. In the free body diagram, next we want to put in the forces that are acting on our penny, our book, our block, whatever. First we have the gravitational force vertically downward. This would be the weight exerted on the object by the earth. We also have the surface of the incline pushing up with a contact force perpendicular to the surface, pushing straight up, not straight up, perpendicular to the surface. That'll go along the positive y-axis. We'll draw this force in this manner. That's the normal force exerted on the object by the ramp or incline, whichever you choose to call it. Thirdly, we have if the object is not moving, it's at rest, we will have a static friction force uphill, and for that we will draw an arrow uphill along the x-axis, and this will be static friction exerted on the object, again by the incline. So the incline is exerting two forces. It's exerting a perpendicular contact force, known as the normal force, and a tangential contact force, static friction, which prevents the slide of the object down the hill. Alright, now when we did the penny example in class, the first time we did it with the penny in the book cover, we were looking at a situation that we would call impending motion. What does this mean? Impending motion means that the object is on the verge of sliding. If the incline becomes any steeper, it starts to slide. So we're kind of on the edge, just on the verge of sliding. That again is known as impending motion. Looking at our free body diagram, we have one off-axis force, which is the weight. And what we're going to do is we're going to break it into its parts. We're going to basically draw a right triangle to show those parts and put them in. Along the negative y-axis, we will have the y part of the weight, known as Wy, that component of weight. And acting downhill, parallel to the incline, or the x-axis tilted, we have the x part of the weight, Wx. That replaces W with its parts. Now, what you had to do in the little experiment in class was to figure out the angle theta at which the penny would start to slide. So, that angle we're going to call theta sub s for static friction. Over here in the force diagram, let's draw that angle a little, just to show it in the diagram a little bit. There it is there, theta sub s. And that angle is the angle in between W and the y-axis. So here's theta again, right there, theta sub s. Now, let's write our force equation. Since we have impending motion, we have balanced forces. And since we've resolved the weight into its x and y components, we can now write our force equations. What we will have, along the y-axis, we will have a normal force upward balancing the y part of the weight downward along the negative y-axis. Uphill we will have static friction balancing the x part of the weight down the ramp or incline. And what we can see here is we have a situation where the net force equals 0. We have a Newton 1 situation of static equilibrium. Now, we're interested in finding out the coefficient of static friction. Okay? And you might at this point be interested in knowing, well, what would be the mass of this object? What would it be? Because if we knew it, we could find the weight of the object, and that would be its mass times g. Well, let's see if that's necessary. It might not be. So what we have here is we have our static friction equation for on the verge of sliding. We have Fs max equals the coefficient of static friction, mu sub s, times the normal force. We want to solve for mu sub s. Just checked it off. Let's do some algebra. Solving for mu sub s, dividing both sides of the equation by the normal force, we'll find that mu sub s, the coefficient of static friction, equals Fs max, maximum static friction, divided by the normal force. Well, what we know from our work in the free body diagram is that Fs max, which is Fs actually, equals Wx, and the normal force equals or balances Wy. So we're going to substitute, and what we're going to see here is that Fs max equals Wx, and now if we think about Wx and what that equals, we can look at a little bit of trig here, and Wx would basically be, it's opposite the angle theta s, so that's going to be the sine, so Wx equals W sine theta. So Wx is simply going to be W sine the angle theta, and that's theta s, an angle which would begin to slide. We can also find that the normal force equals Wy, and using a little bit of trig we find that that's Wy is adjacent to theta s, so that's going to be Wy with a little bit of trig equals W cosine theta s. So we'll put that in for the normal force. Normal force equals Wy equals W cosine theta s. That will be W cosine theta s. Well, by inspection we can see in our equation that the weight of the penny, the block, whatever, cancels. So it's not really necessary to know the mass. So this was actually not needed. If we look at things, we can see from the trig and the algebra that it's gone. Now, so we know that mu sub s equals the sine of theta sub s over the cosine of theta sub s. But if we know our trig identities, we should recognize that sine theta over cosine theta equals the tangent of theta. So mu sub s equals the tangent of theta sub s. So bringing all that down, we have mu sub s equals the tangent of the angle of the incline. At this point, if you know your angle measurement for when things start to slide, you can put that in. And you can find your coefficient. You can do the same analysis over again with when you raise the book and let it tap, you'll find the angle at which it's tapping. So with a tap or tapping, you can find the angle at which the penny or an object would start to slide. So that would be theta sub k. And basically you would do the same analysis. The only thing that would change is this now would be kinetic friction uphill, Fk. And you would get the same analysis. And the shortcut gets you down to this, that mu sub k would equal the tangent of theta k. And that's the angle at which the penny, the object, whatever, starts to slide while you're tapping the incline as you raise the incline. So there you have it. U sub s equals tangent of theta s, the angle at which things just start to slide without tapping. U sub k, the coefficient of kinetic friction, equals the tangent of theta k, the angle at which things begin to slide and then slide with steady motion while you're tapping.